Okay, can the people on Zoom see the slide and hear me okay?
Yes.
Thanks. All right, so what we're going to do today is we're going to talk a little bit about acid-base equilibria, chapter 16, and start on that. And then after about 20 minutes or so, I'm going to stop, and then you can take quiz number 3. You can log on to Canvas and take quiz number 3, which covers chapter 15. So acid-base equilibria. So we've been talking about equilibria in general, and now we're going to focus a little bit more on acids and bases. And so the first thing we want to do is just talk about what is an acid and what is a base. And there's a few different definitions for acids and bases, and so we're going to go over a couple of those. The first is the Arrhenius acid-base definition, and the Arrhenius definition says that an acid is a substance that when it's dissolved in water, the hydrogen ion concentration of the solution increases. A base is a substance, when you dissolve it in water, that you increase the hydroxide ion concentration. So acids increase the hydrogen ion concentration, bases increase the hydroxide ion concentration. One thing about the Arrhenius definition is it only applies if you have aqueous solutions. And so if it's not an aqueous solution, then one of the other definitions applies. One of those other definitions is Bronsted-Lowry. And with Bronsted-Lowry acids and bases, acid-base reactions involve the transfer of protons. And proton and hydrogen ion, H+, those terms mean the same thing and are used interchangeably. So in the Bronsted-Lowry definition, you're talking about how those protons are traveling. They're either being donated, or being accepted. So an acid is something that is a proton donor. So in other words, it gives up a proton. A base is something that's a proton acceptor. So in other words, it receives that proton. So once again, just to go over the difference in the two, if we're talking Arrhenius definitions, we're talking about increasing the concentration of hydrogen ions, if it's an acid, and increasing the concentration of hydroxide ions, it's a base. And the Arrhenius definitions only apply if we're talking about aqueous solutions. So the Bronsted-Lowry acid-base definitions can certainly apply if it is an aqueous solution. So it still works in that. But it also works in non-aqueous solutions. And that's where you talk about what's happening with the protons, what's happening with the hydrogen ions associated with molecules. If the compound donates a proton or loses a proton, gives up a proton, however you want to think of it, it's an acid. If it accepts, it's a base. And we'll see some examples of compounds that fall into these categories in a little bit. So water is interesting because, as we'll see, in this case, it's a proton acceptor, but it also can be a proton donator as well. So, and here what we see is an example of at the bottom. We see water, H2O, accepting a proton, a hydrogen ion, to form H3O plus. So that's another thing. When we talk about hydrogen ions in an aqueous solution, we're really talking about H3O plus. Now, the reality is people usually don't write out H3O plus, they just write H plus. So those tend to be used interchangeably, but technically it's this hydronium ion, the H3O plus, that's being formed in the aqueous solution. Okay, for something to be a Bronsted-Lowry acid, it has to have a proton that it can donate. And you can think of that as a removable proton, a donatable proton, but usually the way it's termed is an acidic proton. And so you can have protons in a molecule, but if they're not donatable, if they're not acidic, then it doesn't serve as a Bronsted acid. A Bronsted-Lowry base must have at least one non-bonding pair of electrons to be able to accept that proton. And in this case, we see the water molecule has two non-bonding pairs of electrons there. So non-bonding pairs of electrons, if you remember, those are just electron pairs that aren't involved in a bond. They're sitting out there free. They're more commonly called lone pair of electrons. So water has two lone pair of electrons, that's symbolized by the 4 dots that you see on it. And so that allows it to be able to accept that proton from, in this case, hydrochloric acid, HCl. Another common proton acceptor is nitrogen. So nitrogen typically will have lone pair of electrons around it. And so nitrogen functional groups tend to be basic. They pick up a proton from a proton donor. Because water can either accept or donate protons, it's called amphiprotic. And so in this case, we see NH3, ammonia, and water. The ammonia in this case is picking up the proton to form NH4 plus, and the water is donating a proton. So in this case, water is actually serving as an acid for the strong base ammonia. So water's interesting. Water has a lot of interesting properties just in general. This is just another one of them, the fact that it can serve as an acid or a base. In other words, it can donate protons or it can accept protons. When we talk about acids and bases, we think of them as acid-base pairs. And the term that's used is conjugate acid-base pair. And what this means is you have an acid or a base, and then after it either donates the proton in the acid case or picks up the proton in the base case, you have the conjugate of that. And so in the example we have on this slide, we see we have HNO2, nitrous acid, we have nitrite ion in the product. So the HNO2, the acid form, donated that proton to water, giving us H3O plus, and then NO2 minus. So the NO2 minus is the conjugate base of the HNO2 acid. And then in this case, the water is acting as a base in this reaction, and its conjugate acid then would be H3O plus. So you always have that association of the acid-base pair. And it's typically simply just one form has the proton, one form doesn't have the proton. When you have those when you have acids and bases, we talk about that some acids are stronger than others and some bases are stronger than others. When we say something is a strong acid or strong base, really what we're saying is that it dissociates, sometimes fully, but at least close to fully. Okay, so it goes back to, we've been talking about equilibrium for a while now. What strong acid or strong base really means is that the equilibrium is just really shifted all in one direction. So for a strong acid, we're saying that all the protons from that acid get shifted to water. So in other words, in the HCl example, all the HCl equilibrium shifts to where it's all hydronium ion and chloride ion. The conjugate base in that situation of a strong acid really has very little basicity to it. And once again, that's because that equilibrium just pushes all in one way. We say something is a weak acid if it only partially dissociates. And what happens then is, and this goes back to, once again, our equilibrium discussions, is if it's a weak acid, you have some of the material stays in that protonated acid form, and then some of the material is now in the conjugate base plus free hydronium ion. And so the conjugate of that conjugate base of that weak acid will also be a weak base. And that, once again, comes back to the equilibrium of things. So if it's a weak acid or weak base, there's only partial dissociation. So you don't have an equilibrium that's pushed real far. And so if it's that way going forward, it's going to be similar coming back the other way. There are some compounds that have negligible acidity, even though they have hydrogen in it. But that would be a case of where that hydrogen ion really doesn't have much acidic character. So in other words, it doesn't really want to be donated. In that case, the conjugate base will be real strong. And so ammonia is an example of that, of what we looked at a few moments ago. Here's a table that shows, certainly not all the acids and bases, but a few acids and bases to give you a feel for which ones are strong and which ones are weak. If we look over on the left-hand side of the acids, we see some of the strong acids: hydrochloric acid, sulfuric acid, nitric acid, HNO3. Then we kind of have a next tier. And what you see here is we see sulfuric acid, H2SO4, is a strong acid. And sulfuric acid, after it's donated one of its protons, now we have HSO4 minus. That's kind of a strong acid, but it's not as strong as the acid before it's donated any protons. So what that means is that first proton is donated a lot more easily than the second one. And we'll get into some of that stuff a little bit later. But that's pretty common when you have acids like that that have more than one donatable proton. You'll see a range of strength of the acid. Phosphoric acid, H3PO4 is another one. There you have 3 protons you could donate, and you see the first one, H3PO4. You go down the table a little bit more, weaker acid is H2PO4, HPO4 minus 2, and then it would go even lower, but it's not on this table. On the right-hand side, we see the bases. And on the base table, it's the ones at the bottom that are the stronger bases. Realistically, the bases that we would be concerned about mostly would be like NH3 is a pretty common base, phosphate a little bit, acetate here you see in the middle, that's the CH3COO minus. But what I want you to notice on this is that the way the table is written is left-hand side is the acid, right-hand side is the base. And for instance, at the top, HCl is the acid, strong acid. Its conjugate base is Cl minus. So all these are paired up acid with conjugate base. And what you see is strong acids have their conjugate base is really weak, and then vice versa. So that's the takeaway on that, and that's what we were mentioning earlier. So this just matches up some common acids and bases so you can see that. Okay, in acid-base reactions, we talk about equilibrium, and the equilibrium favors the transfer of the proton from the stronger acid to the stronger base to form the weaker acid and the weaker base. And in this example here, we have hydrochloric acid, HCl, which we know is a strong acid, and we have water, which can be an acid or a base. In this case, it's going to be a base because it's going to receive that proton from the HCl. And water, H2O, we know is a stronger base than Cl minus. How do we know that? Because we go back to what we just looked at here, and we remember that HCl is a really strong acid, so Cl minus is a really weak base, okay? So the reaction wants to go this way. The proton from HCl wants to go with water to give us H3O plus, and then we're left with Cl minus. So in this case, the equilibrium, if we looked up that equilibrium constant, we would see it's really big. It's much bigger than 1. If it's bigger than 1, then that tells us there's more products than reactants. Products, remember, H3O plus and Cl minus would be the products. So that tells us that the concentration of the hydronium ion and the chloride ion, that portion of the numerator of our equilibrium constant would be a lot bigger than the HCl in the denominator, which tells us it's dissociated a lot. The second example, we have acetic acid, which is CH3COOH. This proton over on the right is the acidic proton in this case. The 3 protons next to the carbon, the CH3 there, those are not acidic. And in this case, we're going to once again donate the proton to the water to give us H3O plus CH3COO minus. That's the acetate ion. Acetate is actually a stronger base than water, so more of this will stay in the acid form of acetic acid. So the equilibrium will shift that way a little bit. And so when we talk about a weak acid, and acetate is considered a weak acid, this just tells us that we're still going to have some concentration of the acetic acid, the CH3COOH, and we're going to have concentration of H3O plus, and then the acetate ion as well. But since the equilibrium constant is less than 1, once again, products over reactants to write that equation, since it's less than 1, it tells us that the concentration of acetic acid in the acid form is going to be greater than this product of hydronium ion, acetate ion. Okay, So I think I'm going to stop there unless anyone has questions, and then we'll pick this up after spring break is over. So if there are no questions, then I'm going to end the lecture part, and you can go ahead and go into Canvas and log on and start the quiz. Okay, thank you.
Thank you. Have a good break.
You too.